Hello and welcome to chemistry. So today we're going to tackle the beginning of module 4, the first section of module 4. We're going to go all the way to experiment 4.4 in your textbook. So please open your textbook to page 99. Remember to take notes, to work through all the examples that I provide and the extra practice problems I provide as well. And if you have questions, please email me during the week or during our virtual meeting, ask whatever you need to ask. Okay. So what does the module cover? We're going to learn some more about how to classify matter, classifying changes that occur in matter. We're going to learn about physical changes versus chemical changes, phase changes in matter, the kinetic theory of matter, chemical reactions and equations, determining whether or not a chemical equation is balanced, and balancing chemical equations. So lots and lots of interesting things. Page 104, I'm going to start with that page because it has a summary of what you're going to be learning in this module. And I think it makes things a little bit more clear if you have this map in front of you. So figure 4.2, page 104. Also, we're going to talk about figure 4.1 on page 100. Matter, all matter, and remember we learned about what matter was in module 1. That's what chemists study. Anything that occupies space and has mass is matter. Learn about that already. Then matter can be divided into mixtures and into pure substances. That's the first division in matter. We're going to start learning about what mixtures are, and then we're going to go into learning about what pure substances are. You actually have already covered pure substances. You covered these in module 3. We talked about compounds and elements. That's what a pure substance is. But we're going to review it a tiny bit. So new mixtures. So matter. You have to answer this question if you want to know if something is a mixture or it is a pure substance. The question is, can it be physically separated? There are two kinds of ways that you can separate matter. One is by physical means and the other one is by chemical means. Chemical just means that you have a reaction. And sometimes you can separate compounds. I mean, you do separate compounds into elements, like in a decomposition reaction. But physical means you're not using a chemical reaction. Okay? You're not changing the nature of your substance. You're using maybe magnetism, maybe you're using filtration, maybe you're changing the state, like gas, liquid, or solid of the substance that you are trying to classify. So for you to be able to classify matter into mixtures or pure substances, the first thing you need to do is answer this question. If it can be separated by physical means, it's a mixture. If it cannot be separated by physical means, then you're dealing with a pure substance. Let's learn about mixtures first. Mixture, okay. There are two kinds of mixtures, homogeneous versus heterogeneous. And this is going to be explained in more detail in other slides. But by the end of the module, you have to have this very clear in your head. Not only do you need to understand how to divide substances and the definition of each one of them, but you will need to be able to give me examples of each kind of substance. Mixture. The next question you need to be able to answer is the composition uniform? So basically, when you look through that mixture, does it look the same all over? That's going to be a homogeneous mixture. Homo means the same. Geneous mixture means that when you look at it, it will look the same everywhere, no matter where you look at it. And I'll show you some slides with examples. Heterogeneous, on the other hand, is a mixture where you can see the little pieces of the different elements that make the mixture present. So you can see that it's made out of several parts. You can see it with your eyes. Heterogeneous mixtures further can be divided into colloids and suspensions, and we're going to see what that means. So substances, pure substances, remember, cannot be separated by physical means. You cannot use magnetism or filtration or heating it to make it go into a gas state. You cannot do any of those things to separate it. The only way to separate them is by chemical means. So if it can be decomposed meant broken apart by chemical reactions. If it can be decomposed, it's a compound. You're dealing with a compound, and we'll learn what compounds were in Module 3. If it could not be decomposed, then you were dealing with an element, and you had your elements in the periodic table, and you're still learning your elements and their symbols. So this is what this module is all about. Let's talk about mixtures. So specifically mixtures. So you need to know the definition of a mixture. It's a combination of two or more pure substances. For example, you can be mixing water with salt, table salt. That's a mixture. You have two compounds mixing. You could have two elements mixing. So you need to have at least two things in there together. If you remember what the definition of a pure substance was, you had your elements, atoms only of one kind, compounds, different atoms that are bonded together. Please remember, you're going to be taking a test on this week, so hopefully all this is in your head already. In mixtures, components are physically combined. So you dissolve something like salt in water, sugar in milk, whatever. You dissolve something or you put it together by physical means. But you did not have a chemical reaction. So they are together, like in this instance, you have several minerals all together in this container. Okay? You can see the little parts. So this is heterogeneous, this mixture, but you have different things put together and you can pick them up and separate them by the kind of mineral it is. So by physical means you can separate this mixture. You also could go through a little shift and the smaller from the bigger, but by color and the kind of mineral it is, you could separate this. Okay. What else? When you have mixtures being heterogeneous or homogeneous, it doesn't matter what kind of mixture you have. Each component of the mixture retains its own identity and properties. So for example, if you mix iron and sulfur, which are two elements, two pure substances from the periodic table, you mix it together, the iron is still magnetic. So you can use a magnet to take it out of the mixture. So you put those in a little container, you stir it with a spoon, it looks black and yellow, but you can take the iron out by using a magnet because this iron has retained its property of being magnetic. Now, mixtures can be separated by physical means, and in a minute we're going to see all kinds of physical means that you can use to separate mixtures. Here you have your sulfur. We're talking about this is yellow. This element is yellow. Your iron fillings are black, and here's your mixture, okay, of sulfur and iron fillings. And actually, you do have a picture of something very, very similar on page 100. So this is where you have that picture. You have put them all together. You can use that iron and the magnet, the iron property of being magnetic, and a magnet to actually take the iron out of that mixture. They were mixed by physical means. There was no chemical reaction whatsoever. Everybody kept their own properties. They were just together in the same space. Mixtures are just that. Different pure substances being a compound or an element that are together in the same space. Now, We talked about physical changes versus chemical changes. You need to have this very clearly differentiated in your mind. Okay? Matter can go through physical changes or it can go through chemical changes. Physical changes can be reversed. Okay, sometimes it's a little bit harder to reverse than others, but they are usually reversible. And chemical changes are harder to reverse. There's a chemical reaction, and oftentimes it cannot be reversed very easily. And when you, not you, but a substance goes through a chemical change, they become something else. They become something else because we said a chemical change was a rearrangement of atoms to become a new substance. So the properties that they had at the beginning are not the same properties they have at the end. Now, you need to be able to give me examples of physical changes. Melting ice. Melting, going from a solid to a liquid state is a phase change, is a physical change. Chopping, breaking anything. When you break something into smaller pieces, that is a physical change. The shredder, right here, that paper being shredded, is a physical change. Mixing anything. This you have green and gray marbles mixed together, so you mix solids like we had the rocks mixed together, but you could be mixing a liquid and a solid. By evaporation, you could take the water out and be left with a salt, for example. So these are examples of physical changes, and some of them are more easily reversed than others, but they can be reversed. Like you can make paper out of other paper. That's what we do when we recycle paper. Chemical changes, examples, burning wood. You're going to be learning that this is a combustion reaction. Rotting, anytime that you have anything rotting, bacteria digesting dead matter, that is also a chemical change. It becomes a different substance. Here you have mixing vinegar with baking soda. This kind of mixture, okay, we talked about mixtures, but when you do that, you don't have them separate. The baking soda and the vinegar do not keep their properties. They're not still vinegar and baking soda. They become something new. Okay, so you don't have. You have a compound. You're making a new compound here. And fireworks. So examples, you have to be able to give me examples of both. There you go. So physical changes, methods of separating mixtures. Mixtures, remember, you have pure substances being elements or being compounds. Doesn't matter. You have some kind of pure substance, at least two, occupying the same space. And mixtures can be separated by physical means. Sometimes easily, sometimes a tiny bit harder. So what kind of methods can we use to separate components of a mixture? Magnets, we saw that a minute ago. A filter, like if you have water and sand, you can have sand here. The filter keeps the sand here and the water here. If it's still dirty, you can filter it again and again and again until you have pure water. The decant, this is the decant, so it's a different kind of filtration. So you're using heat, and the vapor, the steam, when it goes through this tube, it condenses and you pick up the water at the end. So pure water is at the end. It's a little bit cleaner water than doing just filtration by itself. But you can start with filtration and then use a decant to finish filtrating that. So you can combine different methods to finish separating your components. Evaporation, that's the same kind of thing. A centrifuge is a machine that goes around and around and around, and as the machine goes round and around, gravity pulls heavy things to the bottom and leaves the liquid at the top. You may have seen centrifuge machines before. Chromatography has to do with different substances travel at different speeds, so you're separating them by the speed in which they travel through different mediums. And distillation is another one that's very similar to this method. So physical means be able to give me a few examples. Now, types of mixtures, we mentioned them before, but a little bit more clear here. The two major types of mixtures are heterogeneous and homogeneous mixtures. Homo means the same, hetero means different. For anything, okay? You're going to hear those words in other places. You attach them, those prefixes, to other parts of the word, and it just means different or the same. Now, this is a homogeneous mixture. If you look any section in this beaker, looks the same all over. You only see like blue water in there. There is no little pieces of anything floating in there. Looks the same everywhere. That is a homogeneous mixture. On the other hand, in this beaker, you see particles of different colors. Very easily, you can see the particles of different colors. You have heterogeneous mixture there because you can see easily that it's made of different things. Other examples of homogeneous mixtures: air, the air around you. In a minute, I'm going to show you a slide in which we're going to talk about air a tiny bit more. Blood, if you just spill blood, is red all over. You don't see little pieces of anything, although you know it's made out of cells and plasma and all kinds of things in there, okay? Saturated sugar water, so if you dissolve anything in water, sugar, salt, maybe chocolate milk, if it looks the same everywhere, it's homogeneous, as simple as that. Other examples of heterogeneous mixtures, you have your rocks, your oil, and water. So if you put those two together, you'll see that they separate with the oil at the top and the water at the bottom by density. We did an experiment that was similar to that in module 1. Soup. Wow. So you can see the pasta floating, and the veggies are floating in there. The oil, sometimes you can see some bubbles of oil in there. So you can see that it's heterogeneous. And of course, pizza. You have all the ingredients of the different parts of the pizza with the pepperoni and the peppers and olives and whatever else you put in the pizza. Now, sometimes we can make heterogeneous mixtures become homogeneous. Something that is very clearly made out of different components. We have a process that will make them look the same everywhere. Milk is a substance that can be homogeneous. I cannot say this word very well. Homogenization means to make it homogeneous. So homogenization is the process of making something look the same everywhere. But when the milk comes out of the cow, raw milk right here, you can see the different watery components at the bottom and then fat at the top. Most people would not want to drink this kind of milk. It looks kind of yucky with them. Well, to me, it looks kind of yucky. So what they do is shake it to make those fat particles be very, very tiny. They break down. And there are tiny fat particles in here. It's just that they're so tiny that we don't see them. So the milk looks the same everywhere. It went from being heterogeneous to being homogeneous. And that's explained to you on page 104. You have the word homogenized. So that's what it means. On that page, you have other examples of mixtures, okay? So you have cereal and Italian dressing as examples of heterogeneous mixtures. Another examples of homogeneous mixtures, you have Coca-Cola and salt water. So you need to be able to define the difference between heterogeneous and homogeneous mixtures, define what a mixture is, and give me examples of all of them. Okay? We said that air is also a mixture. It's a kind of a homogeneous mixture. Most of the time, if you don't have a fire that has smoke and little pieces of things floating in the air looks the same. Okay? It's transparent. You can look through the air and not see any kind of particles. I mean, if you look sometimes around a window, you can see some dust floating. But most of the time, air looks the same, but it's a mixture of gases. You're going to find a pie very similar to this one on figure 4.3, page 105. A funny thing, we may not realize this, maybe you have learned this in biology before, is that the majority of the air around us is not oxygen. We need oxygen to breathe, you know that. Plants give us that oxygen that we need to breathe. And we release carbon dioxide that plants use to do their photosynthesis and create the sugars that we eat and so on. You should have learned that in biology. But the majority of the gas around you in the air is not oxygen, it's nitrogen. Nitrogen is a kind of a gas that does not hurt us. We breathe it in all the time and we just release it out again. It does not do anything inside of us. Just when we take a big breath of air, 78% of that air is nitrogen, but we don't have any use for it. So we release it back out when we breathe out. Other gases that are present, these are just a few of them, are argon and carbon dioxide, of course, and other kinds of gases. So some of the gases are poisonous. So ozone and other gases are poisonous, but they're in such little quantities that usually they do not hurt us. Now, it's important for oxygen to only be 20% of, almost 21%. In your pie on page 105, you have 21%, but it is almost, you round it up, it's 21%. It's important for oxygen just to be this amount of oxygen because too much oxygen would damage our lungs and also give us blindness. So the air around us is perfect for us to breathe and animals to breathe, just the way it's supposed to be. So know that too much oxygen is poisonous too. Now, we just covered mixtures. So if you have questions about mixtures, talk to me about it. Now we're going to talk about, well, not just now. We covered pure substances in module 3. So this next section should be kind of a review for you. But we're going to concentrate a couple of slides on pure substances. So remember, if it can be physically separated, you have a mixture. But if it cannot be separated by physical means, you have a pure substance. And then you have to question yourself and say, can it be decomposed, broken down by chemical means? You do chemical reaction, decomposition reaction. Can it do that? Yes, you have a compound. Okay? And we talked about how the lowest kind of compounds are the ones that break down into elements. So when you could decompose those compounds, you go back to being an element. Okay. So review. What is a pure substance? You have compounds and elements. Remember, the elements are in your periodic table. You have more than 100 of them. 92 occur naturally in nature. And they are just atoms or molecules. Elements can be atoms or molecules. Most of them occur in atom form. And when you have lots of those atoms, of only that kind of atom, you have an element like this sodium right there. This sodium and a sodium looks like this. And of course, this is made out of many, many, many atoms, but all of them are identical, are atoms of sodium. But you could also have elements in the molecular form. I told you that there were a few, and you're going to be learning about them and memorize them, which ones they are, because you're going to need to memorize who is diatomic mononuclear, meaning having two atoms of the same kind that forms a molecule in nature. They exist as a duo, two atoms together, like oxygen and hydrogen and others that you're going to have to memorize. So they can sometimes exist in the molecular form. Compounds, remember that compounds are atoms of different elements bonded together. Minimum of two different atoms bonded together. And they always have a definite ratio, because if you change the ratio, you have a new compound. We'll learn about all of that in module 3. And here's an example. Sodium chloride is your table salt. So it's not the potatoes here, but the salt that you put in here. So here was your sodium. That's the atom sodium, the element sodium. But here, together with the chloride, will not behave like the sodium because both of them are kind of poisonous by themselves. But we eat salt. We put salt, it's not the best thing for your health, but we do eat salt. And we need some salt to survive too. So when they are together, they become a new substance with new properties because now you have a compound. Now, pure substances, I cannot say it enough, do not separate physically, okay? You cannot use a magnet or filtration or any of the things that we mentioned before when we're talking about mixtures. You cannot do any of those processes to separate the different substances that make a pure substance or compound. This right here is on page 100, the second part of figure 4.1, is sulfur and iron that went through a chemical change, becoming iron sulfide. If you remember before when we had iron and sulfur, it was a yellow substance with some pieces of iron mixed in. Well, no, this is not the same. This is something new. They chemically bonded with one another, and now they have become iron sulfide. And iron sulfide is not magnetic. You cannot use a magnet to take the iron out of it. This new substance has new properties. So it does not behave like the elements that compose it. It's something totally new. Okay? So there you go. You could maybe use chemical means to decompose it using a decomposition reaction. Some of them can be decomposed and some are a little bit harder to decompose, and we're going to be learning about that in subsequent modules. So please, please, please know the difference between pure substances and mixtures. Here's another example. You have gold, only atoms of gold present right here. So this is an element. Right here you have manganese dioxide. So this is a covalent, remember covalent substance because it has that word D. So when you name it, you already know it's covalent. It's a compound. It has manganese and oxide, 1 to 2. Okay? So this is what we need to be able to do extra practice problems number 2 on page 571. So we're going to take a minute to try to do that with the information that we have covered. Okay, let's see if you were right, because this was just a knowledge kind of questioning. There was no math involved here. So number 2, if you have not done it yet, pause, try number 2. Now I'm going to give you the answer. Number 2 said, classify the following as an element, a compound, a homogeneous mixture, or a heterogeneous mixture. And this is something that you're going to have to be able to do, okay, after today. So A, a bowl of milk and cereal. Well, you can see the milk, you can see the cereal, you know it's a mixture. What kind? Heterogeneous mixture. B, a bottle, that's an acid, sulfuric acid. You don't even need to know that that's an acid, but it's a compound. That is a compound. So because it's not just made out of one type of element, you have a chemical formula right there. So you know that that's a compound. C, a copper wire. If you have a wire that's only made of copper, copper is an element. So you have an element with many atoms of just copper. And then D, Kool-Aid dissolved in water. If you have ever seen Kool-Aid before, you know that the water turns the color of the Kool-Aid that you're using, purple, red, or yellow, whatever. But it looks uniform everywhere. So you have a mixture of the Kool-Aid powder and the water, but it's homogeneous. It looks the same everywhere. So that's the kind of thing that you need to be able to do with information that's been presented so far. Now, you will be doing an experiment this week, experiment 4.1 on page 101, in which you're going to be separating a mixture of sand and soap. So I hope you have fun. If you have questions about it before you turn in your lab report, please remember to ask anything you need to ask. experiment 4.3, you're going to be doing as well this week. So you're going to do an experiment that will help you cement in your brain the difference between chemical and physical changes. So you're going to be doing an experiment about that. Now, let's talk about physical states. What's a physical state? That's the natural state of a substance at room temperature and 1 atmosphere of pressure. That's the definition of physical state. All matter exists in one kind of physical state. It can be a solid, it can be a liquid, or a gas, or a plasma. Plasma, you don't hear about plasma very often, but we have plasma as well. At room temperature, which is 25 degrees Celsius, and 1 atmosphere of pressure, which is the general type of pressure around us, okay? Pressure changes with the weather and changes depending on where you are in altitude. But at room temperature, 1 atmosphere of pressure, all things in nature, all matter exists in one type of physical state. Iron at room temperature and 1 atmosphere of pressure, its natural physical state is solid. Water at room temperature and 1 atmosphere exists as liquid. Air around us that we breathe at room temperature and 1 atmosphere is a gas. And we're not going to talk much about plasma, but you need to kind of know what plasma is. So hopefully you remember this from physical science, but here is a tiny bit of review. A solid is just molecules or atoms arranged in regular repeating patterns, held firmly in place, but believe it or not, all solids, if you have atoms or molecules, vibrate. Everything in nature is moving. It's crazy, but it's true. Physicists have proven this to be true. It's just that they cannot vibrate very much because they are very close to each other. They don't have a lot of energy for vibration. Now, in liquids, on the other hand, you already know that they take the shape of whatever container they are in. They flow easily around one another. Those are moving around, being atoms or molecules. They are kept from flying apart by attractive forces between them. And they move faster than they did when they were in the solid state. Because as you're going to see in a minute, substances can move from one state to another by increasing or decreasing the energy they have, which we give by giving them heat or taking away heat. We're going to look at that in a minute. And of course, we have gases. They fly in all directions, those gases. If they can, they just escape. They are so far apart that the attractive forces between them are very insignificant. Because if they had forces attracting each other, they would not be pulling apart. And they'll take as much space as they can. And plasma, that's your last kind of physical state for matter. At very high temperatures, stars, okay, atoms lose their electrons, which we have not yet covered what an electron is in this course, but you probably know from physical science. The mixture of electrons and nuclei from the atoms is plasma. Okay? But you don't really need to know about plasma. I'm just reading it to you because it was in the slide right here. We're going to concentrate on those 3. Now, phase changes. You probably know about this already. So this is not going to be very complicated. Page 109. You have your solid, your liquid, and your gas. All substances in nature exist in one of those states, okay? But you also can change the phase of a substance by increasing or decreasing the energy they have. You do that by adding heat or by taking away heat. So let's study this for a minute. The process from going from a solid state to a liquid state is called melting. And you need to know that. If I say, what is melting? Well, it's going from solid to liquid. The process of going from a liquid to a gas is called vaporization. Okay? And you go through the process of boiling first. So boiling is that process in which you still have liquid, but it's turning into vapor. Then gases can go from the gas state into a liquid by a process called condensation. And the process of going from a liquid to a solid is called freezing. So you need to know those 4 names and what they mean. And how do you do that? Well, just add heat. If you want to go from a solid to a liquid, you are adding heat. Keep adding heat and you're going to go into the gas state. Where does the heat come from? Well, you can make a fire underneath the substance. You can give it some energy in the form of a flame. Or a lot of times, this heat in the air. We already talked about this. The ultimate energy source is the sun. The sun can heat the air, atoms and molecules, and that heat can be then passed on to whatever substance they touch. So if they touch this ice cube right here and transfer some energy into it, it will melt eventually, even if you don't have a flame underneath it, just by the heat that's in the air coming from the sun. So you can go reverse direction. You can use the reverse direction by taking away heat. So the heat is actually leaving into the surroundings. It's leaving, okay? You can go from the gas to the liquid into the solid. Now, new words that you may never have encountered before. Sublimation. Sublimation is the process of a solid going directly into the gas state without passing through the liquid state. That sometimes happens if the amount of heat that's added is really, really, really great. Like a big fire makes the water go from solid form into gas. And the opposite, going from a gas directly into a solid without passing through the liquid state, is called deposition. So there you go. Another thing you need to know, of course, is if I say to you, of the 3 states, which one has the most energy? Well, the most energy is the gas state. Remember that when we add heat, we're adding energy. Heat is a form of energy. It's kinetic energy. These are moving fastest of all the different atoms and molecules. The fastest moving atoms and molecules are in the gas state. And of course, they will occupy the most volume. Volume just means the space they occupy. So a gas molecule or atom is trying to get away from other gas atoms and molecules because they're moving so fast. They have so much energy. They're bouncing all over. And they'll expand. And that's volume. Which one has the least volume? Well, the solid. This one is in the middle. And they move the slowest. They just vibrate. And they have the least energy. So you have to be able to compare. If I say to you, of liquid and gas, which one has the most energy? You would say the gas. Of the solid and the liquid, who has the most energy? The liquid has more energy. If I say to you, of the solid and liquid, which of the 2 has particles, atoms or molecules, whatever it's made out of, moving the fastest? Well, the liquid moves the fastest if you're just comparing solids and liquids. But if you were comparing the liquid and the gas, then you would have to say the gas moves the fastest. So study this because this is going to be in a quiz or a test. Now, another experiment. Lots of experiments. There's a lot of experiments in this module. But I like experiments. I hope everybody enjoys the hands-on because that's what science is about. It's not just about learning about information. It's also practicing what you see. Helps you memorize things. If you put your mind and your hands together, it makes it easier for you to memorize. That's called being a kinetic learner. So page 110, experiment 4.3 says condensing steam in an enclosed vessel. This is going to be extra credit to do at home if you want to. You don't need to do this if you don't want to, because not everybody is going to have this enclosed vessel, which could be an empty paint can, but it needs to be very well cleaned. Please read it very carefully because you don't want explosions. I mean, I don't want explosions. Now, let's see. The kinetic molecular theory of matter. This is explained to you on page 111 of your textbook. Okay. And this theory, okay, is used to explain the behavior of matter. It says, postulate just means it says, that matter is composed of small particles. You already know that. They are atoms. Each particle is in constant motion. And we said that solids just vibrate, liquids are moving a tiny bit more fluidly, although they have forces that keeps them together, and then gases have the most energy, and they just bounce around like crazy. Okay? That's what it says. This is kinetic energy. Kinetic energy is energy of movement. They are moving, so they have kinetic energy. You also know that all matter in their bonds contain potential energy. We learned this in Module 1. That is due to attraction, because some substances do not have bonds the way you think bonds, like exchanging electrons. They just are together because of having charges, and you're going to learn all about that. Don't worry too much. Ionic compounds and covalent compounds have different kinds of bonding. You're going to be learning about bonding very shortly. So instead of bonds that keeps them attached, they have attractions because they have different charges. And sometimes they're not attracted, but they're repulsed, so they move far away from one another. That should make sense, because some charges are positive and some are negative, and they act just like magnets. Opposites attract, and same kind of charges repulse one another. So particles move faster as temperature goes up. What happens when you are increasing the temperature? Remember, the temperature was an indirect way of measuring heat. Indirect way of measuring heat. So what you're actually doing is increasing the heat. And heat was kinetic energy. You're giving them kinetic energy. If you're giving them kinetic energy, they have more energy to move. That's what they do. They move. So less energy for a solid, more energy for a liquid, crazy energy for a gas. Particles transfer energy during a collision with no net energy change. Okay? So if you have atoms or molecules in a gas bouncing all over, they collide with the walls of the container, if they're in a container, and they collide with one another. And the energy is just exchanged. Overall, there's no change in the energy. So there you go. That's what this kinetic theory of matter states. This section of the module did not have a lot of math. So there's a lot of conceptual stuff you're going to have to learn. You're going to have a quiz on it. But remember that I usually make the first section of the module smaller than the second section of the module because you have a test this week. So this week, you're going to read your textbook for this section, add to your notes if you need to, review all examples if you need to, work through all on your own. There's a few of those. As you encounter them and correct them as you go so you don't make the same mistake over and over. Study for that conceptual weekly quiz I provide for you. Do all labs. You have several of them. If you want extra credit, do the extra credit one. Study and take your test if you have a test assigned this week. And we're still learning elements, so continue learning those elements, but all of that is going to be in the homework page. So I hope you have a good week, and I'll see you next week.